Afternoon, everyone. Who's enjoying the motion of the ocean? Well, it only woke me up 14 times last night. We're in the front of the ship, that pounding and crashing. But it was okay. I guess I should have been a sailor instead of a pilot to get my sea legs. So today's tie offering is a what? Anybody? So this is my professorial look. Yeah, yeah. So we have a new look each day or a new story for a tie. Today we're going to talk about our solar system. We started with the first lecture of the realm of the galaxies. What a big story out there, billions and billions of galaxies. Then the next lecture was, let's bring that into our own galaxy, the Milky Way, and what does the Hubble Space Telescope and other telescopes see. Today I want to talk about, let's come even closer to our one sun, our one star of 200 billion stars in the Milky Way. And let's talk about our planets and our sun and our solar system. And I'll have both a combination of Hubble Space Telescope photos and some spacecraft photos that I hope you'll learn some new things. Real quickly, remember our Milky Way, if we were on Andromeda, looks something like this, what's called a barred spiral with very distinct spiral arms coming out of it. Our sun is right here, about 2/3 of the way out from the center. That is actually good news. The center of our galaxy is a very high energy, high radiation, very active part, and the fact that we live 2/3 of the way out in a less active part is very good for life as we know it. It takes our sun, our star, right here, 200 million years to make one rotation around our Milky Way galaxy. Our sun, of course, dominates our solar system. It is 99.9%. What is that, ivory soap? 99.9, are we old enough to remember that one? It has most of the mass of our solar system. The planets have very small percentage of that mass, and of course Jupiter is the largest. Here's some numbers about how many kilograms and how many times Earth the mass is, and etc. The sun is 75% hydrogen and 23% helium. That adds up to 98%, and only 2% is the rest of the stuff that we see in the sun's atmosphere. And in the core of our sun, it is taking two hydrogen atoms, fusing them together at temperatures like 75 million degrees and extremely high pressures, making helium. Then it can take helium as the star, as it burns up the hydrogen fuel into helium, it can start making carbon, then oxygen, the other elements, all the way up to element number 56, iron. Once we get to element 56 in the core of the sun, this fusion process stops, the core begins to collapse, and our sun will expand or explode into what's called a nova or a red giant, depending on the mass. The heavier, larger stars explode in supernova, extremely bright, that create all elements after iron that later can condense into second and third generation stars. Stars evolve based on their initial mass, which is down here, and their luminosity, which is a big word for their brightness, their absolute brightness. Our sun fits right in this area. Notice that I have colors: lower surface temperature, higher surface temperatures, blue, white. Sirius, a famous star, and here's I can't quite see it, but Sirius is up here somewhere in the blue-white. Our sun starts here. We have a class of giants, supergiants, and white dwarfs at the very end of a star's life. So what happens, we believe, is our sun will stay here about 10 million years or so. It'll expand as it burns its fuel into a red giant for a couple of billion years. Then it can explode and become a planetary nebula, and then it will come back down here where the core part of the explosion becomes a small white dwarf star that can last for billions and billions of years. But it is basically a collapsed star. That's what we think the path of our sun. We think our sun is 4.5 billion years old, so it should stay in this main sequence for some significant amount of time yet. Our solar system, not to scale, just to show you the general, is a sun, Mercury, the first planet, Venus, our sister planet, Earth, Mars. Jupiter is the big boy of our solar system, and honestly, of the 2% that remains for the 0.1% of the solar mass in the planets, Jupiter is the majority of that, more than 9/10 of that remaining. Saturn, Uranus, Neptune, and poor demoted Pluto, and other things out here that we'll talk about in a few minutes. I'd like to give you a sense of the relative sizes of our planets, and then I would like to keep going out and give you a sense of planets to stars, our star to other stars, and just give you this kind of relative size to show you that our sun, our star, is a very ordinary star and not really the biggest boy on the block. But here are what are called the rocky planets or terrestrial planets. The other ones are gas giants, but we have rocks and terrestrial. Earth being the largest, Venus about 8/10 our size. Notice Mars is only about 6/10 our size, Mercury smaller, and finally Pluto is about this size. Now let's jump and compare the rocky planets with the gas giants. Here's Jupiter, here's Saturn. Jupiter is so large that we could put 10 Earths across its front face and have just a little bit of room left over. Uranus, Neptune, and now look what happened to Earth, Venus, Mars, Mercury, and Pluto. Now let's compare these planets to the size of our sun. Here's the sun, look at Jupiter. Here's Saturn. Earth has now become so tiny that we almost can't see it. And of course, Pluto is barely a pixel. Now, is our sun, how does it compare to other types of stars? And let's look at a couple. Here is the bright star Rigel in the constellation Orion that I talked about. That would be Orion's left kneecap. Here's the huge giant star Betelgeuse, Orion's upper right shoulder. Notice they're different color. Aldebaran is another famous star in the constellation Taurus. Here's Sirius, the brightest star in the sky, is the 3 stars of the belt of Orion. Point to the lower left, and that's Sirius, the dog star, which is the brightest star that we see with our naked eye or any telescope. But look at the sun. The sun has disappeared on this scale to barely a pixel. Now, are these the largest stars? Let's talk about Antares. Let me go back right here. Here's Antares, a very, very large supergiant red star. If it were in the center of our solar system, here is the orbit of Mars. Here's the surface of Antares. So Earth is where with respect to Mars, inside or outside? Inside, so Earth is down here. We would not exist as a terrestrial planet. These temperatures are so hot that it, of course, melts rock, and then it turns rock into a gas, and then it excites them into a plasma. So this Antares is so big, it would consume most of our solar system. And here's our sun right here with respect to Antares. We've even found a larger star. It's called Uy Scuti, and we can't even see our sun on this scale. It's 9,000 light years from us, 30 times more massive, 1,700 times the sun's radius, and it would reach almost to the orbit of Saturn. That's how big this star would be. Let's look at our planets. Mercury, of course, is the inner planet in our solar system. It rotates around the sun every 88 days. It's about 1/3 the Earth's distance. Mercury is exceptionally dense, meaning that it formed where a lot of the iron was, and then as the star's radiation burst into form, it blew away the lighter elements, and only the very dense elements remained. It has a large iron core and a small magnetic field. The other interesting thing about Mercury, as outer objects, asteroids and comets, approach the sun, the closer they get to the sun, the faster that they go. And if they impact the surface of Mercury, their speeds are so high that they do damage like this. This is probably something, this object the size of an automobile, and it has spewed secondary craters, vaporized the rock, and made this extreme pattern of secondary debris that came out of this crater because the velocities are so high. Venus is our cousin, nearly our twin in size and mass, but the interesting thing about Venus is its surface pressure is 92 times higher than Earth, almost 100 times higher. Any scuba divers in the audience? For every 33 feet that you descend in the water, you increase 1 atmosphere. So multiply 92, let's make it easy, 100 times 33 feet. The surface pressure on Venus is equal below the Earth's ocean to 3,300 feet or so of pressure. That would crush almost anything we send there. On top of that, the surface temperature on Venus is hot enough to melt lead. It orbits in 225 days. Its atmosphere is thick sulfuric acid, and there are clouds constantly around Venus. We never see its surface optically. We have been able to take the Magellan spacecraft launched by the space shuttle, orbited Venus and took these radar images, and we know that Venus has volcanoes and a cratered surface. We don't know if its surface is active like the Earth. There's no evidence of liquid water on the surface of Venus. Only one country has been able to successfully land a surface probe on Venus. It was by the Russians in 1982. This is a picture of the surface. Notice it has rocks and layers. Things are flatter than they are on Earth because of the high pressure. Basically, this lander was a huge spherical ball, and the temperatures and pressures are so high that it only survived for under an hour and sent us back a handful of pictures. Venus, because it is inside the Earth's orbit, has what are called phases like our moon. Remember when Venus is opposite the sun, called superior conjunction, it is fully round circle like our moon. As it moves in its orbit, now it's a half-shaped Venus, a crescent Venus. When it's between us and the sun, it's an inferior conjunction, goes through new moon or new Venus, morning sky, and a half. So Venus switches every about 160 some days from morning sky, very, very bright, to evening sky. Venus is the third brightest object in the sky. The number one brightness, of course, the sun. Number two, the moon, and then Venus, and then the star Sirius. Earth is the third rock from the sun. It's the largest. Here's its diameter, about a little under 8,000 miles. Everybody knows we orbit in 365.26 days. And what's important about that 26 days, what happens on our calendar every 4 years? We add a day so that we don't lose track of what's summer, winter, and fall, and we don't plant our potatoes the wrong time, and it's because of that 0.26 days. Our speed around the sun in orbit is an astounding 66,500 miles per hour. That's 100 times faster than the jets that we fly on. Commercial airliners, 100 times and change. Here's the distance, 93 million miles. It takes light from the surface of the sun 8 minutes to get to us here at orbit, on Earth's orbit. But we define within our solar system a new yardstick called an astronomical unit, and it represents the average distance between Earth and the moon. So for example, instead of having this number with a whole bunch of zeros for Saturn, we say that Saturn is at 9.5 astronomical units, almost 10 times further away from the sun than us. Earth, we believe, is 4.5 billion years old and is in an orbit about our sun, what we call the Goldilocks zone, or a zone where the temperatures allow liquid water to exist with our atmospheric pressure. And for life as we know it, I say carefully because there can be life that we don't know about, but life as we know it needs liquid water to thrive and to exist and to change. Earth's rotation axis is not always pointed in the same direction. Remember when we were kids and we spun the tops? You had the little thing that went up and down and would spin the top. What happened when the top started to slow down? Its rotation axis does what we call precesses, and it wobbles. And what happens is the Earth's rotation axis wobbles over a period of 26,000 years. Right now, our rotation axis is pointed at Polaris, which we call the North Star. In about 3,000 years ago, it was pointed at Thuban. About the time of Christ, it was here, now Polaris, and it makes this big circle with respect to the stars. In 14,000 years, it will be pointed very close to the very bright star Vega, which is a navigational star. Our moon is 1/4 the Earth's diameter, 1/85th of our mass. It takes about 29.5 days to orbit. It's believed to have formed about the time of the Earth, when a planet the size of Mars, not the current Mars, but one that was in or near Earth's orbit, impacted the Earth and struck it so hard at a glancing blow that it spewed out tremendous amounts of Earth's surface material, rocks and other things, into orbit about the Earth that later coalesced into our moon. 3 billion years ago, long before we were here, it was much closer to Earth, but because the Earth's liquid water slowly adds energy to the moon, and the moon is receding from the Earth at about 1.5 inches, 1.5 centimeters, that's 3/4 of an inch, if you will, per year. So the moon is actually moving away from us, and its period is increasing. The other thing we observe about the moon, tremendously large impact craters. Right here is one. And these lines that go straight from this impact crater go halfway around the moon. See this white line right here? That's secondary impacts from rocks that came out of this tremendous impact and are now coming back down and making lines that go halfway around the moon. This is craters called Copernicus. I added this one after the fourth blood moon in 2015. Why is it called a blood moon? Because it turns red. When the Earth's shadow Earth is in front of the sun, and the moon moves through its orbit behind the Earth, it begins what's called a lunar eclipse, and these pictures are taken 10 minutes apart. The camera is fixed, And notice during the night, while this eclipse was happening, this is total eclipse. Now it comes out of eclipse and now the moon is physically moving in its orbit, coming out of the Earth's shadow. And this is what happened because the Earth is rotating. This is the actual path of the moon in a time-lapse photograph that's all photoshopped together, but that represents what the moon looked like over this 3-4 hour period. This is Dallas, by the way, which is 3 hours north of where I live in Texas. Here's Earth seen from Apollo 8, December near Christmas of 1968, and here's the lunar surface. The Apollo 8 spacecraft is in orbit about the moon, and as they came around the backside of the moon, they had an Earthrise, and I honestly believe that this picture has changed our perception of the Earth forever because it looks so distinct out there. Now, is anyone a member of the Flat Earth Society? No hands went up? Do you think this picture would have any influence on their belief system? No. I wonder why that is. Their minds made up. Don't confuse me with the facts, right? Columbus, when he took off to the west, you fool, you're going to go out there and fall off the surface of the earth. There's no question that the earth is round unless you don't believe in this picture is real. Here's Mars, half the radius of Earth. Takes just under 2 years to orbit the sun. It is in an elliptical orbit. In other words, it is 1.4 times the Earth's distance at its closest point to the sun and 1.7 times the Earth distance furthest away. Its orbit is only Pluto and Mars have these significant differences from a circular orbit. Mars has mostly carbon dioxide. These are the polar caps of Mars. Its surface pressure is equivalent to being on Earth at 100,000 feet. That means its pressure is 1/1000th that the pressure on Earth. About 1/100th the pressure on Earth. If you were on top of Mount Everest, you're at 30,000 feet, and you know how thin the atmosphere is there. So the surface pressure on Mars is so low that our astronauts and cosmonauts will have to wear supplemental oxygen and a pressure suit. It's not completely a vacuum, but the pressure's too low for us to be able to stand outside, even if it were warm enough on the best day at the equator, which is maybe 40 or 50 degrees centigrade. So liquid water does not exist on the surface right now. We have clear evidence it existed in the past on the surface, so Mars has had a major climate change. Notice this is taken from what we call the Mars Reconnaissance Orbiter, a beautiful spacecraft with a large telescope on it that looks down and sees this incredible detail. It's about 200 miles above the surface of Mars, and this is a Mars dust devil in the desert taken from Mars. We also see pictures of this canyon called Mars, the Valles Marineris. It is so large that if Los Angeles were here and New York City is here, 3,000 miles away, it is 5 miles deep. Compare that to the Grand Canyon, about 1 mile deep and nowhere near as long. Tremendous rift in the surface. There are 3 major volcanoes here. And one called the Mount Olympus Mons. I want to show you a picture of that. It's 82,000 feet tall. How tall are volcanoes on Earth, roughly, give or take? They aren't 80,000 feet, are they? They're, 15,000, 16,000, Mount Rainier, 14,000 is something. Mars has ice glaciers covered with thick dust. Our Mars Reconnaissance Orbiter has taken radar data that shows ice glaciers hidden under very thick dust layers, and we think there's enough ice. This is a computer-generated image in the northern hemisphere where under a mile of dust we think are these large glaciers, and the dust is protecting them from evaporating away. So we know that there was at one time a lot of water on Mars. After Mars comes what is called the asteroid belt. It's a large group of asteroids that we think should have coalesced into a planet, but the next planet out is Jupiter. Jupiter's gravitational field is disrupting these asteroids, and we think keeping them from coalescing and forming a new planet. There's a lot of them, and we have recently sent a spacecraft from Earth to, and we launched here, and then we went out, flew by Mars to get a gravity boost, and that took us further out. We arrived at Vesta, a large asteroid, circular asteroid, in July of 2011. We departed in September, and then we continued to go out till we reach Ceres, which is the largest asteroid. How did we do this? We have what's called a high-efficiency ion thruster. And what that means is we're using 10 kilowatts of electricity from the solar cells. We accelerate xenon atoms in an electric field, and we spit them out of a rocket nozzle. It doesn't produce much thrust, 2/100ths of a pound. That's barely enough to feel if it touched you on the head. And but the interesting thing, though, is I cannot lift off the surface of the Earth with an engine like this, but I can change from one orbit to another orbit by continuously thrusting, and its propulsion is nearly 10 times more efficient than chemical propulsion. So the way that we would envision we would use this type of engine is we use the International Space Station or something like it as the St. Louis, where we gather our wagon trains, we provision them, we man them, we check them out, and then with ion engines, we can go to Mars. This type of engine would only exist in orbit. In other words, would never come back up or go down to the surface of the Earth once we deployed it. So it's a different transportation stage from orbit to orbit. It's 10 times more efficient than our best engines. Here's Ceres in a Hubble photo. Here's the Dawn spacecraft has discovered a crater with 2 bright white spots in the middle. We hope that that's ice, but we're not sure yet. They're still doing science. It's very unusual. Here's Vesta, and you can notice, even with the Hubble Space Telescope, that was our best photograph in 2004. This is what we saw at Ceres in 2011, and the Vesta is at Ceres now doing significant science, which is right here. Ceres. Jupiter, 5th largest, 2.5 times the mass of all the other planets combined. And remember, they are only 0.2% of all of the mass in our solar system. It's 318 times Earth's mass. It rotates even this big in 10 hours. It has mostly gas, hydrogen, helium, some methane, and other ices of carbon gases or carbon molecules. We have the great red spot right here. Interestingly enough, this spot, it's so cold out at Jupiter in the upper atmosphere that Galileo, when he invented the first telescope, discovered this red spot in around 1610 or so. And it is still rotating. We think it's a giant hurricane-like feature or storm. And the reason that Jupiter has belts are these gases are moving in belts that are moving different directions. This one's moving this way, this one's moving this way, and because at the interaction of those 2 jet streams moving in opposite directions, it often forms features like this that can last for hundreds of years. There are four. Jupiter has many, many satellites. The four major ones were, in fact, discovered by Galileo, and he gave them the names of Io. They're all Greek gods and goddesses. In this case, goddesses Europa, Ganymede, Callisto. Io is close enough to Jupiter, and Jupiter's gravitational field is so powerful that it is constantly squeezing and releasing Io as it orbits around Jupiter, causing its inner part to be liquid. And we are actively seeing, when we first flew the Galileo spacecraft by, it saw this feature, which is the plume of an active volcano as I see it from the edge. As it rotates around, the plume looks like this. So what I've done is I've blown up. These two volcanoes were erupting at the same time at Io. Here's this one on the edge, and this is the one that we see in the surface. We believe that Europa has a liquid saltwater ocean. And it is so cold at the surface it's frozen, but the tidal forces of Jupiter cause the frozen block to shift and make these cracks. And then the water will well up inside, and it's so cold on the surface it refreezes, but it can have a different color from different things that are happening in the ocean. The next place that we would like to send a probe searching for life is a probe that can land on Europa, use uranium radioactive thermionic generator to melt its way through the surface, go down and swim in the ocean, and take pictures and radio at the proper frequency through ice. What does it see on Europa? Ganymede also, we believe, has liquid water under its frozen surface. Callisto, notice how cratered its surface is. It's been struck thousands and thousands of times. Here's the evidence that we have from the gases that are coming off of Ganymede, interacting with Jupiter's very, very large and powerful magnetic field, and that they are indicating that there is a saline or saltwater moon water below Ganymede's crust, and causing these auroral belts from analyzing the physics of and the chemistry of how what these belts look like. Europa actually has plate tectonics. Instead of land and earthquakes, it's going to have ice quakes, because we don't think it has rock structure. We think that it actually has continents of ice moving around each other from the tidal forces. Saturn is the sixth planet, a gas giant, 95 times Earth's mass. Galileo saw these rings, but didn't know what they were. His telescope wasn't powerful enough to resolve it, so he put two little lobes out to the side. Notice that the rings are in the rotational equator of Saturn, and it is one of the most magnificent sights that you will see with your own eyes through any telescope. You'll never forget it. Saturn is one of those must-look-at things that you see. There are some amazing, there's a hexagonal polar vortex at Saturn's North Pole because of opposite moving bands of gas, that their interaction at the jet streams moving in opposite directions has caused this pattern, which looks just like the cell of a honeybee, right? This is where honeybees store their honey, in a hexagon. So this is a very popular, in terms of strength and other characteristic, shape, a hexagon shape. Here it is around the North Pole with a black and white photo, and now a color enhanced photo blowing up this area to show you that remarkable feature with a core vortex in the center. We also have seen with Hubble this is a storm starting in 2010 as it progressed in the northern hemisphere of Saturn in 2011. Look how it's spread out over the entire northern hemisphere over just under a year. We sent a probe to Saturn called Cassini. Cassini was the astronomer who first discovered this large divide called Cassini's Gap. There's another gap called Encke's Gap as our telescopes got better. We sent Cassini spacecraft to Saturn so that we could understand its moons. It has one very large moon called Titan, the only moon that we're aware of that has a significant atmosphere on it. We'll talk about it in a second. But when Cassini went behind Saturn, and the Saturn is blocking out the sunlight, it does what's called backlighting, or scatters the sun's light into this beautiful, beautiful picture of the rings, and we can actually tell a lot more detail from this backlit scattering. But there's a little tiny thing right at the end of that arrow. Can you see it on that at that resolution? I can see it on mine, but you don't see it up there. I'm going to blow that region up just for fun. Now do you see it? That's the Earth. That is the Earth that Cassini spacecraft that we human beings sent to Saturn, went behind Saturn. This picture is not an accident. We understand orbital mechanics and where things should be, and they planned to see Earth looking through the rings of Saturn. I find that one of the most extraordinary pictures I've ever seen. I love this photograph. The largest moon of Saturn is Titan. It has an atmosphere of mostly methane. And on this Cassini spacecraft, we cooperated with the European Space Agency, and they included a lander called Huygens, who is named after the Dutch astronomer Christian Huygens, who discovered Titan. It's the only moon with a dense atmosphere. It's mostly nitrogen. I said methane, it's nitrogen. On the surface, we see lots of evidence of frozen ices of methanes and other gases like that. It's about half the mass of Mercury, but it's larger than Mercury. So we know it doesn't have the extraordinary rocky density of Mercury. And it orbits Saturn every 16 days with the same side pointed at Saturn, just like our moon is gravitationally locked, and we only see the front side of the moon. We never see the back side of the moon from Earth. Now, here's some extraordinary photographs. As Huygens was descending about 5 miles above the surface, it took this picture. Here's one a little bit later. What does this structure look like to you? A river. This is a river with tributaries and a delta. This is a shoreline, and this is a lake of methane. Or in Europe you say methane. It's potato, either one. But what's extraordinary is we think that there are rain showers of liquid methane on the surface of Titan, whose temperature is these type of extremes, almost 300 degrees Fahrenheit below zero, 170 degrees centigrade below, and it results in liquid methane oceans, shorelines, and rivers. Luckily, Huygens, when it landed here on land somewhere, not in the ocean, so we actually have these pictures of dirty water ice with dust and ice mixed together, and hydrocarbons, meaning methanes and ethanes and etc., of ice because it's so cold on the surface. Extraordinary pictures. Uranus, first discovered by a telescope in 1781 by William Herschel, 4 times Earth's diameter, 14 times our mass, takes 83 years to orbit the sun, and it's almost 20 times further away from the sun than the Earth. The interesting thing about Uranus, one of many interesting things, is most of the planets are rotating with their spin axis perpendicular to the plane that we are orbiting in, which is an extension of the sun's equator. So when solar systems form, the planets are drawn toward the center like a flat record, and that's where they want to form. And their spin axis tends to be perpendicular to that. Something struck the Earth long ago, perhaps causing the moon, that tilted our spin axis 22.5 degrees, 23.5 degrees. So we have seasons. Interestingly enough, current Mars is also tilted about that. Jupiter, Saturn, Neptune, they're rotating with their spin axis perpendicular. Here's Uranus with its spin axis slightly below the plane of where the planets rotate. So it's tipped over more than 90 degrees. And so half of its orbit, at one time its northern hemisphere is pointed at the sun. On the opposite side of the sun, its southern hemisphere is pointed at the sun. And then it gets its spring and fall, where its equator is pointed at the sun. It must have extraordinarily different seasons and weather patterns than we do from the heating from the sun. Not sure why it tipped over. One guess is it got hit by something really big that tipped it over, and maybe it absorbed it and became bigger. Neptune was the first planet discovered by predicting tiny, tiny differences in Uranus's orbits, so that where we thought Uranus should be, it wasn't quite there. And what was happening was we predicted that there's another planet outside of it that is impacting Uranus's orbit, making these tiny, tiny differences. And that was predicted by a French mathematician. And it was discovered in 1846, very close to the prediction of Leverrier. And it's 4 times larger than Earth, and there's some of the math. It takes 165 years. The further you go from the sun, the longer it takes for the planet to make its orbit. 165 years. It is 30 times further away than Earth. So let's go back for a minute. Jupiter's about 5 to 6 times further away than us, than Earth. Then I have Saturn 10 times. Then I have Uranus 20 times further. Now Neptune is 30 times further from the sun. Its atmosphere mostly hydrogen, helium, and these ices of water, ammonia, and methane. It does have a large moon called Triton that we also want to investigate. Pluto, discovered in 1930, reclassified in 2006 as a dwarf planet of the Kuiper Belt. Pluto is actually a binary planet system. It has a moon Charon. Here's Pluto. These two objects orbit about a common called the barycenter that's dependent on the mass. If Charon on Pluto were exactly the same mass, they would orbit about each other right where my arrow is. Because Pluto is bigger, they orbit about right here, but that center of rotation is outside the surface of Pluto. And we honestly think, with our new findings from the New Horizon, here's the relative size of Earth, Pluto, Charon, they are orbiting about a point about right here. Both of them orbit about that point. And we think that the tidal forces from that not having the primary planet in the center and the other one going around it is causing Pluto to have an active surface. These are photographs from the New Horizons spacecraft that went by earlier in the year. We expected to see an inactive, heavily cratered terrain, and it is very active, very few craters. These mountains are 11,000 feet tall. We think that Pluto is like Titan, has these methanes, hydrocarbon ices, and water ice, and perhaps it's liquid like Europa down in the center via a mechanism we don't understand. But we think that perhaps these tidal forces and then the ice floating on a liquid surface is allowing these huge continents of ice to move and create mountains just like our Appalachian range. The other interesting thing on the surface of Pluto that we have never been able to see from Earth, only with this spacecraft, took 10 years to get there. Look at the color difference between this region of Pluto and this brighter, probably some type of ice reflecting the light. And there are not anywhere near as many craters as we expected. A huge and unexpected finding that's keeping us busy trying to figure out why. Here's its large moon Charon. This is an area that looks like our moon with the dark material that was some type of early in the formation large crater, then filled with the liquid. This feature right here is a mountain, and it has what we think is a huge moat around it with some of these hydrocarbon ices. Extraordinary photos, and we never would have seen this detail without sending the spacecraft. Let's go even further. 30 times further from the sun than the Earth is Neptune, and then we have Pluto, which is out here, and in a distance called 30 to 50 times the distance of Earth to Sun, what's called the Kuiper Belt, where there are large numbers of small remnants of the solar system that created Pluto and created Charon, and they are orbiting out there at very, very large differences. So one of the people asked me, why was Pluto demoted? I don't know I wasn't at that meeting, or I'd have voted no, not to demote it, just keep Pluto. But we have found 4 to 5 significantly large, almost as large as Pluto, other planets outside of Pluto's orbit in this region. And I guess they didn't want to give them new names, so their solution was demote Pluto. Still called Pluto, but it's now called a minor planet. Even further outside. Now here, what you see in this circle is a blow up of the entire solar system and the Kuiper Belt inside here, where all of these objects are in the plane of the equator of the sun. We think that comets come from what's proposed as a Dutch astronomer, that Oort cloud, that has a lot of comet material in the equator of the sun, but much, much further away, almost 1 light year from here to here. And this is light days from here to here, but this is light year. And these objects can be disturbed. They're rock and ice and dust mixed together by stars that are moving outside of ours, 4, 5, 10 light years away, can disturb slightly their orbits, and then they start falling toward the inner solar system. And when they do, they become this: comets. Here's a beautiful comet McNaught in 2007, viewed from Chile. What's happening is, as it moves into the inner solar system, the solar radiation heats it up, melts the ices, spews them off in this tail, and the solar wind gives it this curved shape as it blows that material from away from the comet. Here's Halley's Comet in 1986. I hope all of you saw it. None of us will see it again, because it has a 76-year period, and so that was almost 30 years ago. Unless you live another 46 years, some of you may see it. You won't see Halley again. I was pleased to be able to see it. It's one of the famous recurring comets. This is Comet West in 1976. Very beautiful comet. Now let's talk some. When a comet comes through our solar system, all of that stuff that you saw spewing off of it are tiny grains of sand, very tiny and clumped together molecules of gas. They are trailing out in these orbits. These are 7 or 8 different comets, and behind that comet, in its orbit, it leaves this trail of dust. Every year, the Earth passes through this trail of dust in August and causes what we call the Perseid meteor shower. And a Perseid meteor shower is the Earth moving at 66,500 miles per hour, and it's running into this sands and tiny grains of sand, etc. They enter the atmosphere. Friction causes them to heat up and burns them up very, very quickly. And here's a great photograph of a Perseid meteor taken from the International Space Station in August of 2011 as we passed over Chile. And here's a tiny grain of sand that has entered the atmosphere and makes that meteor shower trail. Even further outside, because the sun has a huge magnetic field, it has this large magnetic bubble around it, and it causes a bow shock, a termination shock. We call this region the heliopause. That means that inside this region, everything is affected by the sun's magnetic field and the solar wind. Outside this region, we don't know what it is, but we believe that in this region, we could actually measure and sample our Milky Way's magnetic field. We would be far enough away from the sun. And there are two spacecraft on the way right now. Voyager 1 is right here. Voyager 2 is right here. We are actually still in communication with large antennas. So we have one in Madrid, one in Australia, and one in California, Goldstone. They are able to contact Voyager 1 and 2. We're getting magnetic information. We're starting to see evidence as they proceed away from Earth and away from the sun, never to return, that we're starting to measure this boundary because we're seeing the magnetic field bounce back and forth. And we're really curious when they get out here in 30 or 40 years, what does the magnetic field of the Milky Way look like? I love this photo. Voyager 1 was on the way from Earth in 1977. When it took this picture, it was just about over Mount Everest, and here's the Earth and the Moon as Voyager 1 sped away toward Jupiter and then on to the outer planets in the 1970s. My first job at General Dynamics in 1975, before the launch in 1977, was to do the trajectory calculations that we put in the Titan Centaur rocket's computer. Centaur was the brains, and it says if you launch this day in this 1 hour launch window, I want your velocity to be this much, pointed that direction, and if you do that, dear rocket, and I tell you to cut your engines off, and you do it properly, you will go to Jupiter. The good news is I got all of that right. Both of them that loaded into that computer had the correct targeting, and they went on to Jupiter and made extraordinary information. Ancients have been watching the heavens for thousands and thousands of years, millennia. Here's Stonehenge. Stonehenge has alignments that measure when the sun comes up at equal day and equal night. It also has measurements that some of these stones, the moon has an 18.6 year cycle. They used it as a calendar and probably some type of worship because they looked at the stars all the time. The Mayans, as far back as 2000 BC, understood lunar cycles, predicted eclipses. They accurately predicted helical risings of Venus. That means when you begin to see Venus as a morning star, or when you are going to stop seeing it as an evening star. There's some evidence because of their 5,600 year major cycle that the Mayans may have understood the Earth's precession axis, which is 5 times that 5,000 year, 200 year major cycle, they call it, of our 26,000 year rotational axis precession. Here's the astronomical observatory at Chichen Itza. The Anasazi ruins at Chaco Canyon have a canyon that the moon rises at a certain time in the year, and they were able to tell with this ellipse where the moon was on 18.6-year rising between major and minor standstills. You'll have to see me at dinner to even get close, because this is a 1-hour discussion. There probably are only a couple hundred people in America that even know that the moon has an 18.6-year period of cycle based on its orbital motion about the Earth. And the Anasazi knew it and understood it. And there's my last slide, and I have maybe time for 1 or 2 questions right here. What was the moon what? Why was the moon red during a lunar eclipse? Great question. The reason is that when the sun, I need a sun, the sun is here, right there. You're the Earth, and behind you, Jim, is the moon directly in line. The sun's light is being refracted through our atmosphere, and that refracted light turns the moon red, just like the moon becomes red when it's looking through the dense atmosphere at sunrise and sunset, and then it's bright when it's directly over here. Good question right here. Yes, sir.
Many of the planets that you described are spinning in orbit.
All of them are spinning.
What's the energy that creates them?
Conservation of energy. When these things collapsed initially, this big disk, call it a record, before I have planets forming, that's about the moon, the sun's equator, is rotating about the sun, just as the sun is rotating. As this material collects and starts to make a planet, it takes that angular momentum of that rotating material and then keeps sweeping more material out, making a dust, collecting the dust as it's gathering mass, but it is capturing the angular momentum from the initial disk of dust that all the planets formed from as they began their formation process. One more question. How about over here, all the way in the back? Yes. Good question. All the planets have a rotation axis, most of them perpendicular to our orbital motion. The question is, do they all spin in the same direction? They do, except for 2 very unique differences. One is Venus, which actually spins opposite very, very slowly. Its orbital period is 243 days, and it's the only one spinning the opposite direction with a period of 225 days. We have absolutely no explanation for that. The other one is Uranus, which is tipped over 98 degrees. The others are generally spinning with my thumb up, representing the North Pole of the sun. So, enjoyed it. Thank you. The next lecture will be about black holes. I remember I said black holes are very important in the formation of galaxies, so I built a new lecture to try to give a little bit more information about what's a black hole. How did we find them if we can't see them? Okay, and that will be the next lecture. Then we'll move on into space lectures, space shuttle, space station, history of the human space flight and the race to the moon. See you at dinner. Anywhere you catch me on the ship, I'm always happy to entertain questions, have fun the rest of the day, and maybe it'll smooth out a little. Thanks so much.